Good afternoon. My name is Randy Armstrong. I'm the chair of the OPC UA Security Working Group, and I'm here to talk to you about the OPC UA Web API and how you can use it to access your OT data in a cloud environment. Now, the OPC UA Web API is part of the cloud initiative. It is a API that's built on HTTPS and JSON, which is the primary language of the cloud today. Most communications that go on between cloud applications are using HTTPS and they are using JSON. It's sometimes called OPC UA via REST. I prefer Web API because it's more descriptive of what it is. I don't have to define what REST is. And you can use it to communicate with UA servers. They could be running in the cloud, they could be running on the factory floor, but you're using the primary language of the cloud, which means you can take advantage of a lot of the existing tools that are available for cloud application development. So it's worth noting that we've talked a lot about IoT and PubSub and how PubSub is the future for cloud communication. And PubSub is great for certain use cases. It is very scalable, provides a level of isolation that works with OT firewalls. It's useful for pushing large amounts of data into the cloud where it can be analyzed by various types of cloud-based analysis applications or even AI engines. It's not so useful for interactive two-way exchanges, which is why so much of the cloud-based communication is based on HTTPS and JSON today, because those kinds of exchanges make up a large bulk of the kind of traffic that has to go on. So sort of dive a bit into the use cases for why you need to have a web API. Data discovery is one example where the results from each step are needed for the next step. You're browsing a tree of information. You browse your first tree. You don't know what your next step is until you've seen the results from the first browse. Then you can pick one of those and go down to the next level and the next level. Configuration, where you're doing any sort of change to the system. This requires some level of transactions and some ability to roll back changes if the entity making the changes disappears or doesn't complete things or doesn't do things properly. Errors need to be reported back to the client so they know that something went wrong. Access control is a must. You can't be allowing changes to the system unless you know who's making those changes. And if you often need to log those changes and you need to tie those changes into specific users. That's very, very difficult to do with a PubSub environment with an MQTT broker. A web API is much more suited for those kinds of applications. And the last use case where you'll see the need for a web API approach is when every client needs a unique subset of information. And this can happen because a server has so much information that it simply can't publish everything. It would fall to its knees if it tried to do that. It would be overloaded. And in these cases, every client that connects to that server needs to be specific about what it wants to see. And and so it will create one subset, another client will connect and it will create a different subset. So every client will have a different subset of the data it's looking at. And when that happens, the advantages of PubSub disappear, because if every client needs a different subset of information, then you don't get a lot of the scaling that you get out of broker-based communication, and you're much better off using the Web API approach. Now, the Web API itself provides a set of basic services that could be used to access OPC UA information models. And this duality is fairly important, that we have these generic services that are accessing these models which are consistent across all UA servers and are independent of the protocol you're using to talk to them. And this means is that you don't have to learn a new way to look at the data every time you talk to a different server or using a different protocol because they've decided to map the API, their information onto an API in a different way. No, you've got the generic services. They allow you to interact with the model. The model is the same whether you're dealing with a digital twin sitting in a cloud-based base engineering server, or are you talking to the real device down on the factory floor? It's the same information model, same APIs, same calls, but it's all built on IT infrastructure, HTTPS and JSON. In particular, we're using an open API schema. Now, what is OpenAPI? Well, OpenAPI is a formal standard for describing HTTP APIs. It's widely used in the industry, wide support by tool vendors, widely known by developers and engineers. And the OPC UA Web API is described by an open API schema, which means you can just grab this schema, it's available on GitHub, and you can ingest it into your favorite tools, and you can get up and going very quickly with development using the OPC UA Web API. Now, when we created the open API schema, we didn't start from scratch. What we did is we took all of the effort that we'd already invested in developing the OPC UA specification and simply created an automatic mapping from the existing Part 4 services to OpenAPI operations, as well as a mapping from all the various data types that are defined in the specification onto OpenAPI schema types. And we're also able to do the same for companion specifications. So all of the investment that has gone into developing information models in OPC UA can immediately be used in the OPC UA Web API environment because we've got the tooling to allow you to move in and declare these Open API schemas that can then be ingested by these various tools. On top of it, all of the schemas that we're generating will have links back to the online reference for the OPC UA specification. So you're not only generating a schema, you're generating a schema that gives you links to very detailed descriptions of every element that's in the schema. Now, I want to highlight one important thing about why OPC UA is so important for the OT industry. When we originally had tackled OPC UA, we'd come out of the success of OPC COM, but we realized that tying the standard to a specific technology stack was a recipe for obsolescence. We wanted OPC UA to be adaptable as technology changed. And so what we're doing with this open API schema is we are showing you how all of the effort we put into OPC UA is seamlessly moving to the new technology as technology emerged and it is being used. We're not losing anything from the past. We're making it better. We're making it available. It's making it more useful to end users. And that is something that you really need if you're building any sort of system, that level of adaptability. Now, there's one subtle mismatch between the way OpenAPI is designed and the way OPC UA works. Specifically, OpenAPI is intended for a fixed schema. Basically, everything is known about the schema in advance, and all the types are defined in advance, and they're all in the initial file. And so, for example, you can have the Microsoft Graph API is an example of an API where all of the elements that are within that model, whether it's teams, groups, users, all of these different things, well, they're all well defined. They're known in advance. Users don't come along and create new objects that you can access via the Teams API. In UA, it's different. We want companion specs to come around, and they want to define their own data types. You want to have variables that have, in the example that we have on the right here, an orientation data type that wasn't known to the spec. It's part of a separate companion spec. So we provided tools that convert the CS information models to OpenAPI schemas, and these schemas can be ingested by the same tools that handle the OpenAPI schema. And we've got examples showing you how you can merge this auto-generated code into a single application and take advantage of the tools. So when I talk about the tools, let's take a look at some of them. Postman, very popular one. It's very useful for developing web interfaces. You can ingest the OpenAPI schema definitions. That's why you have all these services appearing in the panel on the right. It gives you the JSON messages that you can just fill in and then hit a button and you can call them and get the response. In this case, it's a simple read request, pass in a node, ask for the value attribute, get back the value. In this case, it's a structured value, but the structured value is defined by a different information model that is communicated with the UA type ID parameter. So the Postman allows you to set up tests, do all sorts of very sophisticated um, sort of automated operation, sort of automated testing operations, and it's generally very helpful to assist developers. The other tool that we made a lot of use of is the OpenAPI generator, which is an extensible tool that generates code from an OpenAPI schema in a wide range of development environments. You basically give it the schema, press a button, and you can get Python code, you can get Rust code, you can get Go code. We've pre-compiled a number of different libraries for TypeScript, for .NET, for Python. We will add more of those as we get feedback from the user group, what they would like to see. But again, because these are all generated libraries based on the OpenAPI schema, it's very easy for anybody to be able to create everything they need to develop a Open API client without having to go out and get a commercial SDK or even worry about getting a open source one. So the Web API Starter Kit is a MIT licensed project that has a number of examples to help people get started with the Web API. It has a server built with C#, and a number of clients that are built using Python, Node.js, React, TypeScript, C#, and all of this code is available on the OPC Foundation's public GitHub. It also includes a sample web application, and this web application is running permanently on a server that the OPC Foundation makes available. The API is published there using a Swagger UI. And it will give you that will give you the URL to use if you want to use it for your own testing. It supports HTTPS and WebSockets, which I'll get into the WebSockets a bit more in subsequent slides. But it's basically a functional OPC UA client that's written completely. It's a browser-based application that has no SDK requirements at all. It's basically using auto-generated code with the Open API generator, and everything is developed with that as a foundation. You could look at it, you can see that it's a relatively small amount of code. Most of the code there is laying out the widgets and making things look nice. Now, one of the things that you'll need to do whenever you're communicating with any servers, you need to authorize a user. And so all authorization with the Web API is done using the standard conventions that are used in the IT world. And that's the authorization header on the HTTP request. And we require support for OAuth 2, which is basically a bearer token, and a basic authentication, which is username and password, which is generally not recommended, but it's a useful fallback when you don't have all of the OAuth 2 infrastructure set up. In the case of this application, it uses OAuth 2. You can, if you log in, you will be redirected to the OPC Foundation website, which is a WordPress instance. You'll be asked to log into that website, and if you happen to have two-factor authentication required, you can go through that, and then I'll redirect back to the application. Then you'll be logged in. You'll be authenticated as whatever your user account was, and that will give you some additional access to the server depending on whether or not you used an account that is a OPC Foundation corporate member or whether or not you used an account that's just a normal member. So, but as you can see, it's fairly straightforward in order to integrate sophisticated authorization mechanisms into your application by simply taking advantage of a lot of this IT infrastructure, which has been in place for quite a while. Now, OpenAPI itself does not support WebSockets. Uh, it's focused entirely on HTTP. However, WebSockets is a very important capability that we wanted to support. So we developed an additional envelope that you can use to send the OpenAPI messages over a WebSocket, and we added some other additional details about how you handle the WebSocket handshake. There were some things we needed to mandate. Now, the WebSockets allow for much more efficient subscriptions. Most sophisticated clients nowadays, web clients, what they will do is they'll attempt to use WebSockets, and if they can't use WebSockets, we'll fall back to using straight HTTP. The OPC UA Web API is designed for that kind of dual mode operation, so that would be a very straightforward architecture for you to implement. Now, as I mentioned in the previous slide, yeah, we created this generic envelope to allow you to sort of bundle up the OpenAPI request and send it out over any transport. That means you can also use the OpenAPI to do request response over a broker. And this comes up periodically. People would love to be able to, they've got an MQTT broker, they would like to be able to talk to a server behind the broker, and MQTT 5.0 happens to have some REST request reply semantics built into the MQTT protocol that you could take advantage of. So basically, the server would publish its request topic, and the client would send the request. And it, and when the client sends the request, what it would do is it would send the response topic, indicating where it would want the response to go. So the server can then process it and send it back to a client. So even if it didn't know about the client in advance, it knows where it needs to send it because it was told in the message where it should go. It's a very simple capability, not a lot, but it's powerful. Now, one of the disadvantages of using the broker is you're going to have more latency, but obviously, if your broker is the only way you can talk to a server that's behind a OT firewall, then it's better than nothing. And it opens up some interesting possibilities for architectures, the fact that you could now do this. Now, a lot of the UA services have been designed to work with a session. So the first thing you do is you got to create a session, and it saves some server-side state it serves some client state on the server, and this client state is used to optimize things like subscriptions, browse operations, a couple other things. Oh, user authorization, it's only done once. It's not done on every call. However, there are a number of basic services that don't actually need any server-side state. These are the sessionless services. And these are read, write, call, and browse. And these don't these can be called directly from the web API without setting up any session, and it makes them very easy to use. And it becomes a single line in order to a couple lines of code you can invoke them. So I've got some Python scripts here, and it also makes it very easy to deploy a UA server in a cloud-based environment where you don't care, you no longer care which server you're hitting each time you connect to which server in the farm you're connecting to, because there's no state that you care about. It's just each time you hit it, you can get a different one and everything will work fine. Obviously, if you're developing applications and you're using only sessionless services, you're going to take a hit in terms of performance in some cases. So that will be kind of the trade-off you'll have to make. You can always switch to session-based services if it makes sense for your application. But doing quick and dirty stuff with sessionless services, something as simple as making a function, making a method call, can now be done very easily. Uh, JSON was used for ease of processing. Now, obviously, this can cause messages to blow up fairly quickly, so we mandated the need to support gzip, which is going to be supported by most standard client web client libraries. So this is something you get out of the box just when your response is being processed. You don't actually have to do any code, any additional code, because the library itself figures out that the response was gzip encoded and decode and unzips it for you. But this is again is an important feature that allows for optimization and reducing the sizes of the messages, which will be particularly important if you're doing any sort of sending these messages over any sort of broker. So when you're actually looking at deploying the OPC Web API, there's a number of different models you could use. You could have a dual endpoint server where it has the HTTPS endpoint side by side with the UATCP endpoint. So the clients that just support the HTTPS endpoints can come in and use it, and but it's all operating on the same underlying objects, underlying services. You can also have a gateway. This is going to be the most common case because people are going to tend to want to build up a separate application that's designed to be a web-facing application that can redirect calls to UATCP endpoints. You don't get your client authorization because the gateway is a man in the middle, but user authorization. Basically, the client passes the tokens in, which then get passed on to the server, so the server knows who the downstream client is. So you can authenticate properly with the server. An aggregator is a more complex form of a gateway that can connect to multiple OPC UA TCP servers. That is it for my talk today. I'll give you a chance to have any questions that might be in the chat, and I hope you found it useful.